Hi everyone, in this video we are going to be looking at how to write the expression for equilibrium constant Kc and the calculation involving. Now we have two types of equilibrium constants. We have the equilibrium constant Kc, which we are going to be focusing on in this video, and we also have equilibrium constant Kp the next video. Then the third video will now show us the relationship between Kc and Kp and all the calculations involved. Now the equilibrium constant Kc is the ratio of the concentration of products to that of reactants. Each concentration is raised to the power of its number of moles. Each of the concentration will be raised to the power of its number of moles. Now let's look at this. This is a reaction between A and B giving us C and D. The number of moles of A is A, that of B is B, C, C, D, D. Now the equilibrium constant based on the definition is equal to the concentration of C raised to power C, the number of moles, times the concentration of D raised to power D raised to power the number of moles, all over the concentration of A raised to power A times the concentration of B raised to power B. That's the product all over the reactants. Okay, and please, we should note that only gases and aqueous solutions are considered. When you're dealing with equilibrium constants, you're only considering gases and aqueous solutions. You don't consider solids and you don't also consider liquids. Now look at this example here. Write the expression for the equilibrium constant for the following reactions. So we are given all these reactions and we are asked to write an expression for the equilibrium constant. Let's start with A. We have N2. Okay, let's just go straight to the point. The equilibrium constant now for this, for A, is the concentration of ammonia raised to power 2, concentration of ammonia raised to the power of 2 divided by the concentration of nitrogen times the concentration of hydrogen. Now hydrogen is raised to the power of 3. Okay, that's the answer for A. Now what of for B? Let's see. Here the product here is IBr, iodobromide, so we have concentration of IBr raised to power 2. Now divided by the reactant, now we have concentration of iodine times the concentration of bromine. Okay, so let's see for C, the third one. Here we have SO2 reacting with O2 to give us SO3. So my Kc here is going to be the concentration of the product, which is SO3 raised to the power of 2 divided by the concentration of SO2, then times, sorry, this should be raised to power 2. The balance reaction here should be 2, so raised to power 2, then times the concentration of oxygen. Okay, then D. Now I want you to notice something here. Ammonium chloride here is a solid, so decomposing to give us ammonia, which is a gas, and hydrogen chloride, which is a gas. Remember, you don't consider solid, so the concentration of a solid or liquid is seen as just 1. Now that means the equilibrium constant now for this very reaction is going to be the concentration of ammonia, NH3, times the concentration of HCl, actually all over 1. So that's for ammonium chloride, meaning I can leave my answer as concentration of ammonia multiplied by concentration of HCl. We don't consider solids and we don't also consider aqueous solutions. Now let's see the final one here. Also observe that calcium carbonate here is a solid, calcium oxide is a solid, but CO2 is a gas. So my equilibrium constant now, Kc, will be concentration of CO2 if I like, I say times 1 all over 1, okay, which is still concentration of CO2. Okay, so let's move forward. Now look at the second example here. We are told the equilibrium concentrations of nitrogen, hydrogen, and ammonia in a Haber process is 0.2, 0.25, 0.1, 0.2, and 0.25. Calculate the equilibrium constant. Of course, the first thing for us to do is to write out the equation, equation of the reaction, which is N2 gas plus 3H2 gas, giving us now 2NH3, which is gas also. So, and we know now that the equilibrium constant for this, the equilibrium expression for this particular reaction is the concentration of ammonia raised to power 2 divided by the concentration of nitrogen times the concentration of hydrogen raised to power 3. Now at this point we can substitute the equilibrium concentrations. For ammonia here is 0.25, so we are going to get 0.25 raised to power 2. Now divided by, for the nitrogen here is, nitrogen is 0.1, 0.1, then multiplied by, for hydrogen is 0.2, so 0.2 raised to power 3. So when you calculate that, you are going to get, when you calculate that, you are going to get 78.125 mole squared then dm6. You're going to wonder how I got this. It's very simple. Just know that the unit for concentration is molarity, which is molar. So you have molar squared all over, that's molar squared all over molar times molar raised to power 3. So that's going to give us molar squared divided by molar raised to power 4, and that will give us molar raised to power minus 2. And molar actually means mole per dm cube, all raised to power 2, which would give us per squared mole, then dm6, this raised to power minus 2, then dm raised to power 6, because minus 3 times minus 2 is 6. Okay, now we are going to look at, the next thing we are going to look at is calculation of equilibrium concentrations. There is what we call equilibrium concentrations. You know, when reactants combine to form products, the reactant will lose certain amount and the product will gain certain amount in order to establish equilibrium. So in this particular case, we want to look at how to calculate equilibrium concentrations. Now let's see the first example here. Let's consider the following reaction: nitrogen plus oxygen giving us NO, nitrogen 2 oxide. Initially, the concentration for each species is as follows. That's the initial concentration. The concentration of nitrogen equal to concentration of oxygen equal to 0.1. Remember, initially there is no concentration for this, so the value of Kc for this reaction is known to be 0.1. That's the value for Kc. Calculate the equilibrium concentrations of nitrogen, oxygen, and NO. Okay, let's go. Now I want to repeat the reaction. We have N2 plus O2 giving us 2NO. Okay, now we are going to use the ICE method. We have I here represent the initial concentration. So the initial concentration for nitrogen is 0.1, 0.1. The initial concentration for oxygen is also 0.1, but the initial concentration for this is 0 because nothing has been done yet. No product has been formed yet. Okay, now we have the C. C here means the change in concentration. Like here now, this guy is going to reduce. Remember, the reactant will reduce, but the product will increase. The reactant will reduce by X, so we say minus X. Here also, that's for nitrogen, minus X. For oxygen also, minus X. X is the amount by which it reduces. We don't know, so that's the reason why we say X. And you should know that the change in concentration is always the number of moles times X. So the number of mole is 1, so that's minus X. The same thing here, minus X. But here, this will increase, so it's going to be positive, plus. Minus for the reactant, but plus for this. And the number of moles is 2, so 2X. So while this decreased by X, this decreased by X, this will increase by 2X. 2X because of the number of moles. Remember, it is whether the number of moles times the unknown, which is X. Now the E now stands for the equilibrium concentrations. The E stands for the equilibrium concentrations, which is the sum of I plus E. So if we do that, this will be the equilibrium concentration for nitrogen is 0.1 minus X. The equilibrium concentration for oxygen is also 0.1 minus X. The equilibrium concentration for NO is 0 plus 2X, which is actually 2X. Okay, so from this we can say that our equilibrium constant is supposed to be the concentration of NO raised to power 2, that's the product, which is NO raised to power 2, divided by the concentration of nitrogen, N2, times the concentration of oxygen, O2. Now to substitute values from the question, we have that the equilibrium constant for the reaction is 0.1. So in place of Kc, we put 0.1 equal to the equilibrium concentration for NO here is 2X, so 2X all raised to power 2. Now all over the equilibrium concentration for nitrogen is 0.1 minus X times the equilibrium concentration for oxygen is also 0.1 minus X. Now we can say this is 0.1 equal to 2X all squared. Now all over 0.1 minus X, 0.1 minus X can give us 0.1 minus X all squared, since they are the same thing. Okay, so we can have 0.1 equal to since the both numerator and denominator have the same power squared, we can write this as 2X all over 0.1 minus X all now squared. So which, if we to take away, we'll find the square root of this. So we find square root of 0.1, which is now going to give us 2X all over 0.1 minus X. Okay, so square root of 0.1 here should give us 0.314, okay, equal to 2X all over 0.1 minus X, which when we cross multiply, we are going to get 0.314 into 0.1 minus X is equal to 2X. Here we have 0. When we open the bracket, 0.314 times 0.1 will give us 0.0314 minus 0.314x equal to 2x. So 0.0314 now is equal to 2x plus 0.314x. We have 0.0314 is equal to 2.314x. This plus this will give us this. So now x is equal to 0.0314 divided by 2.314 which from calculation, by calculation, it is going to give us 0.0137 molar. Okay, so that gives us the answer. So we can now say that the equilibrium concentration, we are asked to find equilibrium concentrations. Now the equilibrium concentrations for N2 is 0.1 minus x. That means 0.1 minus 0.0137. You can check that. For oxygen is the same value, 0.1 minus x, which is 0.1 minus 0.0137. Then for NO is 2x, which means 2 times 0.0137. Okay, so that is it for that. Now it leads us to the second question. Okay, it says the equilibrium constant for the reaction represented below is 50. So that's the equilibrium constant for this reaction at 448 degrees Celsius. A, how many moles of HI are present at equilibrium when 1.0 mole of hydrogen is mixed with 1.0 mole of iodine in a 0.50 liter container and allowed to react at 448 degrees Celsius? We have to find the number of moles of HI present at equilibrium. That's what we are interested in. Okay, we have hydrogen combined with iodine giving us 2 HI. Now, but I would like to say, first of all, the concentration, the initial concentration of hydrogen is 1 mole. But remember, this is mole. Well, we are given volume, so concentration is number of moles over volume. So we can say the concentration, initial concentration of hydrogen is equal to 1.0 moles all over 0.50 liters. That will give us 2 mole per dm cube. And that's the same thing for that of iodine, 1.0 mole all over 0.50 liters, which will give us 2 moles per dm cube. Good. Now, so we use our ICE for the I, which is initial concentration. For hydrogen it is 2. For iodine, let me use 2.0. For iodine it is 2.0 also. Then for hydrogen iodide is 0 because initially there is no reactant, there is no concentration for product. Now C talks about the change in concentration. For hydrogen, 1 mole, so 1 times x, which is x, and that will be minus x. It is reducing. That's for iodine, it's also minus x. Then for hydrogen iodide is 2x. Now for the equilibrium concentrations, for this would be 2.0 minus x. You add for this 2.0 minus x, then for this 0 plus 2x, which is 2x. So you can say that the equilibrium constant here is concentration of hydrogen iodide raised to power 2 divided by the concentration of hydrogen times the concentration of iodine, according to the formula. You see the formula. Okay, and the question says it is equal to 50. So your HI here is 2x, the concentration of HI is 2x all squared, divided by concentration of this hydrogen is 2.0 minus x. Equilibrium concentration for iodine is 2.0 minus x, all equal to 50. Now this would be 2x all squared. 2.0 minus x, 2.0 minus x will give us 2.0 minus x all squared, since they are the same, equal to 50. I can find the square root of both sides. This will give me 2x all over 2 minus x is equal to square root of 50 is 7.1. Now if we cross multiply, 2x is equal to 14.2 minus 7.1x by cross multiplication. If we collect like terms, we are going to have 2x plus 7.1x equal to 14.2. So that's going to give me 9.1x equal to 14.2. And x now would be 14.2 divided by 9.1. That is going to give us 1.56 molar concentration. Okay, so but the question here, we are asked to find the molar concentration. We are asked to find how many moles of HI are present at equilibrium concentration when 1 mole of this is mixed with 1 mole of this. So we want to know the number of moles of HI. Now for HI, the equilibrium concentration for HI is 2x, which means 2 times 1.56, and that is going to give us 3.12 molar. Okay, so the number of moles now, moles will be the concentration, which is 3.12 multiplied by the volume, which is 0.5. Number of moles is concentration times volume, that is CV. Okay, so and that is going to give us 1.56 moles. Okay, that's the second example. Now we're going to look at the third example. Okay, now question number 3. When 0.40 moles of PCl5 is heated in a 10.0 liter container, an equilibrium is established in which 0.25 moles of chlorine is present. An equilibrium is established in which 0.25 moles of chlorine is present. In this case, they gave us the equilibrium concentration for chlorine, which is 0.25 moles. Okay, and what are we asked to find? What is the number of moles of PCl5 and PCl3 at equilibrium? Now let's see, let's rewrite that solution. Now we have PCl5 giving us PCl3 plus chlorine gas. Okay, now the initial concentration for chlorine, according to the question, is 0.40. These are the products, so the initial concentration is 0. Now we have the change in concentration, which is C. The change in concentration for PCl5 is minus x. That's minus 1 times x. Is the reactant, that's why it is minus. But for the product is plus. The change in concentration is positive. And in this case, it's just 1 mole, so we have plus x. And for chlorine, just 1 mole, so we have plus x. Okay, so the next is the E. Remember, ICE. I stands for the initial concentration. The initial concentration for PCl5 is 0.4. But for the product is zeros, because at that point no product yet. Now, but the change in concentration for reactants is always negative, and for the product is always positive, because the reactants are reducing in concentration, but the products are increasing in concentration. So this increased by a factor of 1 because of 1 mole, while this increased by a factor of 1. This also increases by a factor of 1. Now the equilibrium concentration is adding I with C. So for here is 0.4 minus x. For here is x, 0 plus x is x, and for here is x. But we are told that the equilibrium concentration for chlorine, that is in there, an equilibrium is established in which 0.25 moles of chlorine is present. So the equilibrium concentration of chlorine is 0.25, which is the value for x. So we can say that the equilibrium concentration for PCl5, which is 0.40 minus 0.25, and that's going to give us 0.15. We can, and that's the answer for that. So the concentration of PCl3, the number of moles for PCl5 is 0.15. Then the number of moles at equilibrium for PCl3 is 0.25, which is x. The next question there is, what are the equilibrium concentrations of the three components? Now the equilibrium concentrations here for the three components, remember what we just found is number of moles, but the equilibrium concentration should be number of moles all over volume. Now for PCl5, it is 0.15 all over. Look at the question here. The volume is 10.0 liters, so all over 10.0 liters. And that's going to mole all over 10.0 liters. That is going to be giving us 0.015 molar. Then PCl3 is 0.25 mole all over 10 liters. That gives us 0.025 molar. Then chlorine now. Chlorine is also 0.25 over 10. That gives us 0.025 molar. Okay, so that leads us to the final question, which is to calculate Kc. What is Kc? Remember, I will write the reaction here. We have 3Cl5 giving us PCl3 plus Cl2. In this case, the equilibrium constant Kc will be the concentration of PCl3 multiplied by the concentration of Cl2, that's the product, all over the concentration of PCl5. Okay, so that is going to give us, for PCl3 is 0.25 times Cl2 is also 0.25 all over PCl5, which is 0.15. Okay, and why the unit will be molar times molar divided by molar. So you can check that with your calculator, then write your final answer here.